Welcome to Lesson 10, Volume of Cones and Cylinders for Module 5 Functions. We are going to continue on our theme of volume, and we're going to start by reviewing volume of a rectangular prism. So in this opening exercise, you are asked to write an equation to determine the volume of the rectangular prism that is shown. So work on 1, 2, 3, and 4, and then come back and finish the video, and we'll continue on together. So for this first one, we have that the volume, remember volume is equal to length times the width times the height. And it's defined as the amount of space that a object takes up, or the amount of holding capacity that it has if it is empty. So we have this first one, the volume would equal, so we don't know the volume. We do know two of the dimensions. We do know the length times the width. So we've got 8 millimeters times 6 millimeters times the height. Okay, so we could simplify that to the volume is equal to 48H. And we know that the units are going to be millimeters cubed. But for an equation, volume equals 48H. So continuing on that theme, the second one we would have the volume is 8 times 10 times H, or the volume is 80H. And then for the last one, volume is 6 times 4 times H, simplified 24H. Okay, so if we wanted to write an equation for volume, V, in terms of the area of the base, B, what would we say? We notice that in each of these examples, our number here, 48, 80, and 24, is actually the area of the base. 6 centimeters times 4 centimeters, 10 inches times 8 inches, and so on. So we could say that the volume of a prism is equal to the area of the base. We're going to use a big B for that so that we don't confuse it with, like, base times height in a triangle. So we're going to use a capital B to show that. Area of the base times the height. So if I know the area of the base, I can multiply it by the height, and that will be the volume. Okay, so part B says, using what you learned in part A, write an equation to determine the volume of the cylinder shown. Okay, so they're hinting at we could use the same idea for a cylinder as we did for a prism. And that's going to actually turn out to be true. So what is true is that the volume of a cylinder is equal to the area of the base times the height. So we just need to know the area of this base, which in this case is a perfect circle with a radius of 4. So what is the area? Let's write it down here. What is the area of a circle? Okay, so that's something that we've learned in the past, or we're expected to know. So if you don't know it, you can do some looking up. That doesn't look very good. You can look this up. I have a video, a really nice video that develops the area of a circle. Not that I did, but that is in some of my playlists. I have a playlist called Circles, and it's on there. But area of a circle is pi times the radius squared. Okay, so that's something that we need to commit to memory and understand here. So the volume of the cylinder is the area of the base times the height. So we could say that its volume is pi times the radius, which is 4, squared times the height. So for this cylinder, we don't know the height, so we would say that the volume is 16 pi times h. And the units would be centimeters cubed, because we'll have centimeters squared for the base times centimeters for the height. So that's going to give us centimeters times centimeters times centimeters. So this would be an equation to determine the volume of that cylinder. And we could say the volume of that cylinder is a function of its height, because it has a given base. Okay, so just to kind of recap some of that. So if you look at this prism here, you can see the blue base that it's sitting on, the length times the width, that area. And if you think in terms of little slices just stacking up, and another one stacking up and stacking up, the more height we have, the more volume we fill in, and the more volume it has. So the same thing, so the volume, let's just recap, the volume would be the area of the base times the height. So the greater the height, the greater the volume. All right, so let's talk about cylinders now then. So this figure on the left is kind of an irregular figure, but you can see it has a base and it has height. If you think of perpendicular lines coming up from that base, so in that way it's very similar to a prism, which also had those perpendicular lines coming up from the base. So in this figure, we could say that as we stacked sections of it up, just like we did with the prism, its volume would get bigger and bigger as we included more and more height. And we would just be taking the area of that base, which for this shape, there's no formula for it, but if we knew it and we kept stacking these up, we would have more and more volume. So, but for the figure on the right is more the type of prism that or cylinder that we're used to seeing, where the base is a circle and you could think of these lines or coming perpendicular to the base and coming straight up. So this would be called a right circular cylinder. Where that has two identical bases that are perpendicularly in line. So these come up like that. So we could think of these discs stacking up and adding volume bit by bit. So for this shape then, since the area of a circle is equal to pi times the radius squared, the volume of the cylinder would equal that each of those discs would be pi times the radius squared. And then as we stack them up, we would multiply by the height here to get our total volume. So that is the volume of the cylinder, but really we want to think of it as, we don't want to be memorizing multiple formulas. So it's just the area of the base times the height. Okay, so in a minute we're going to do some examples, and in these examples you're going to be asked to leave your answer in terms of pi. So what does in terms of pi mean? Okay, so if we have a circle here and its area is pi r squared, and if I told you that the area of that circle is 50 and 24/100 inches squared, or approximately 50 and 24 inches squared, and asked what is the radius, how would you figure that out? Okay, so I want to pause and do that calculation now and see if you can figure out what is the radius of that circle. So to do this, I would want to set myself up an equation that said since the area is pi r squared, I could say 50.24 is equal to, and I'm going to use equal to instead of approximately, because I'm going to, I'll know that it's an approximate answer, is equal to pi times the radius squared. And if I divide by pi, I'm going to get the radius squared. So r times r is equal to 50.24 divided by pi. Let me find out what that is. And so if I approximate pi with 3.14, let's put that in. This comes out to 16 because that's what I used for it. So you can see that r is approximately 4 if it's approximately that, right? So we could tell that. But what if I told you that that the area is 16 pi, and what is the radius? Then I would know that 16 pi is equal to pi r squared, divide through by pi, and I would see immediately that r is equal to 4. So sometimes leaving your answer in terms of pi, in other words, not multiplying out. Now notice that 16 times 3.14 is 50.24. But sometimes it's convenient just to leave it here. It tells me a lot about the circle. I can immediately see the radius, and I know what's going on. So there, of course, are times when you're asked to multiply out, use an approximation for pi, but for most of our problems, we're going to leave them in terms of pi, which is really nice. Okay, so let's look at some of those examples. So we're going to work through a few of these exercises, and then we can check them together. Okay, so we're going to do the first 3. There's 2 in a cylinder and another cylinder, and then we'll be talking about cones. So work through exercises 1 through 3 using what you know about volume being the area of the base times the height, and we'll check those together. Okay, so for this first one, we're going to go step by step through it. So the area of the base is equal to 4.5, whoops, wrong color, 4.5 inches times 8.2 inches, 8 2/10 inches, I should say, is equal to the area of the base, which we're going to call big B, right? So that is 36 9/10 inches squared. What is the height? The height is 11.7 inches. And what is the volume of the rectangular prism? So the volume is equal to 36.9 inches squared times 11 7/10 inches. So that's going to give us 431, and these are obviously, well, maybe not obviously to you, but these are calculator problems, okay? Inches cubed. The important thing here is to be able to know how to find the volume, not to be able to do all that multiplication. All right, so let's look at the next one. The next one's a cylinder. So again, what is the area of the base? Well, the area of the base, we'll call it big B, is equal to pi times the radius squared. So that would be pi times 2 centimeters squared. So that would be pi. And this is going to be 2 centimeters times 2 centimeters. So we've got 2 times 2 is 4. Centimeters times centimeters is centimeters squared. So I'll rearrange that to 4 pi centimeters squared is the area of that base. The height is 5 3/10 centimeters. And so the volume is 4 pi centimeters squared times 5.3 centimeters. So this equals, we'll do the 4 times the 5.3, and that gives us 21.2. And then we've got 21.2 pi centimeters cubed. Okay, let's look at the next one. The area of the base. What is the area of the base? Well, the area of the base, big B, is equal to pi times the radius squared. So the radius in this case is 6 inches. So we've got 6 inches squared. So the area of the base is 6 times 6, which is 36 pi inches squared. The height is 25 inches. So the volume is the area of the base, 36 pi inches squared, times 25 inches. So that works out to 36 times 25, which is 900 pi. Inches squared times inches is inches cubed. So the volume, total volume is 900 pi inches cubed. Okay, now we're going to look at cones, and the first one on the left is kind of a general picture of a cone. Remember, this was sort of our general picture of a cylinder, and so the cone is defined in terms of the cylinder. So P is a point somewhere on the top of the cylinder, and then it has lines radiating down to the perimeter of the base of the cylinder. So if you think of every line that could come down from P and touch not just the perimeter, although that will be the edge, but touch every point in the base, every point, filling it in completely, that would be the definition of a cone. Okay, so this is a general cone here. This one over here, because this is a right circular cylinder, this is going to be a right circular cone, where the point P is the center of the circle of the top base, and the lines radiate down to the bottom base, the whole figure. So filling it in totally, and that becomes our cone. Okay, so we're going to again, we don't want to have to memorize another formula for volume. So we're going to relate it to the formula for the cylinder, which remember we related to the formula for a prism. So these are all related. So if you remember prisms, you can work your way back up to cones, which is really, really cool. You don't want to have to be memorizing lots and lots of formulas and filling your brain with that. Okay, so how does the formula for this cone relate to the cylinder? So what we did in class, and what is a fun thing to do, is if you have these figures, there's some manipulative sets that you could use, or you could make your own, although it'd be a little tricky to get it accurate. But what we want to know is how many times would we have to fill this shape or figure to fill up the cylinder. So the bases match and the height matches. So it's a cone with the same height and the same base. How many of these would go in here? Okay, so it's really fun to do, a little bit surprising, but you could do it experimentally, or you can watch a video. So I'm putting up a link to that video. It will also be in this playlist where somebody does it, and you can watch them do it. Okay, so it turns out that 3 times this volume equals the volume of the cylinder. So, so the volume of the cone is equal to 1/3 the volume of the cylinder. All right, so we know the volume of the cylinder is pi r squared times the height. And so that's our volume for the cone. So all you have to remember is that it's 1/3, that 3 of these, get a good color here, 3 of these here filled up will equal the cylinder. Okay, most people guess 2, but it actually is 3. So the volume of the cone is 1/3 pi r squared times the height. And while we're at it, I just wanted to mention that this is a cone also, but notice that the top of it, also called the apex, is not directly above. So this isn't a right circular cone. This would be an oblique cone. It has exactly the same formula. If you use the perpendicular height for the height, you can't use the slant height for that. So it'd still be the area of the base times the height. We won't have any like that, but I just wanted to mention that so you knew that. Okay, so here we have a right circular cone, and you can use the diagram and find the volume of this cone using the formula that we just developed. And you can also work on problem 5. So do both 4 and 5. Go ahead and pause it now and work on those, and then come back and check your work. Okay, so the volume is equal to 1/3 pi times the radius squared times the height. So we can fill in for this one. Volume is 1/3 pi times the radius squared, which is 4. 4 millimeters squared times the height, which is 9. And the units on this will be millimeters cubed. Okay, so what I'm going to do is I'm going to multiply the 1/3 times the 9. All of these numbers are being multiplied together, so just to simplify. And, you could use a calculator on this one, but this one's fairly straightforward. So I'd recommend stretching your number brain. So 1/3 times 9 is 3. 3 times 16, 4 squared is 16, is 48. So we have 48 pi millimeters cubed for the volume of that one. Okay, you could have done it differently, gotten the same answer. All right, the next one. So the volume again is 1/3 pi times the radius squared times the height. So we've got 1/3 times pi. The radius is 2.3. So it's 2.3 squared times 15. And simplifying that, again, you could put this in your calculator. 1/3 times 15 is 5. Then I'd 5 times 2.3 times 2.3, and you're going to get 26 and 45/100 pi. And the units on that will be meters. It's really hard to see on my copy. Meters cubed. All right, this next exercise, it's actually the last exercise, has several parts and pulls together a lot of what we've been learning about geometry. So I think it's important. If the first part of this lesson was fairly easy for you, I think you really need to continue with this problem. If you were struggling, you could probably move straight on to the problem set and be fine. So I'm going to go through it. We're going to go through it together. So what do we know about the lengths AB, and the lengths AO? Okay, so the length of AB, you probably noticed, is the radius, right? And the length AO is equal to the height of that cone. All right, so we should probably read the problem first. Okay, so a container in the shape of a right circular cone has height h, and so here's the height h, and a base of radius r, as shown. It's filled with water in its upright position to half the height. So this water goes up to h/2, half the height. Assume that the surface of the water is parallel to the base of the inverted cone. Okay, so it's held exactly straight up and down. So that water is parallel. Use the diagram to answer the following questions. Okay, so I got ahead of us a little bit. But AB is the radius, AO is the height of that cone. So what do we know about the measure of angle OAB, so OAB, and the measure of angle OCD? Okay, well, we know that the measure of angle OAB is equal to the measure of angle OCD, and that they're both equal to 90 degrees. So they're both equal to 90 degrees because we know that this is a right circular cone, so we know that this height is perpendicular to the base. And we know that the base and the top of the water are parallel to one another. So both of these angles, because of these parallel lines here, are equal, and they are 90-degree angles. Okay, so what can we say about triangle? So now we're talking about triangles here. Triangle OAB, so that would be this triangle here, and triangle OCD, right there. Okay, so we want to think back to one of our earlier modules, and what does this make you think of? If you want to pause it and think about it, that would be good. Okay, so hopefully you could notice that triangle OAB is similar to triangle OCD. And the reason would be angle, angle. So notice that both triangles have angle, this angle O in common down here. And both triangles, we already said, have this angle equal. So they're similar by the angle, angle criterion. So remember, if two triangles have two angles that are congruent, then we know that, we actually know that the third angle has to also be congruent, and we know that they're similar, because any triangle that has all three angles the same are similar. So the angle criteria tells us that they're similar. So what does that matter? All right, so let's read part D. We want to know, what is the ratio of the volume of water to the volume of the container itself? So in other words, what fraction of that container is filled with water? So you might want to take a guess at that. We did that in class. It's filled to half the height. But people noticed, well, but the cone keeps going out like this, so it's definitely not half filled. So think about, what fraction do you think this container is filled? Okay, so in order to find the ratio of the volume of water to the volume of the container, we would need to be able to write an expression for the volume of water and write an expression for the volume of the container. So we know for the container, we know it has height h and radius r. And we know for the water, it has height h over 2, but we're not told what the radius is. So we're going to need to use this fact that the triangles are similar to be able to determine what the radius of the water is, so that we can write an expression for the volume of water there. So again, give that some thought. Hopefully you've made a prediction about what fraction you think it is, and see if you can use similar triangles to figure out what this radius would be. Okay, I just needed a little bit more room to do this. So we know that, that the length of AO is equal to 2 times length OC. Okay, and those are corresponding parts of two similar triangles, right? So we could say that the length of AO over the length OC is equal to 2. And so if that's true, then we would know that the length of AB over the length of CD should also be equal to 2. So, but AB is the radius of the cone, and so length CD is the radius of the water, and so that ratio is equal to 2. So if we rearrange things, we can see that R is equal to 2 times the length of CD, and that if I divide by 2 here, I can see, and let me just take that off so it's not too messy. So I can see that the length of CD, the length of CD is equal to the radius over 2, or R over 2. So this length here is R over 2. Okay, so now we're ready to write the expressions for the volumes. So the volume of the water is equal to, we're going to use the volume of a cone. So it's 1/3 pi times the radius squared. The radius is r over 2. So we want that whole thing squared. R over 2 squared times h over 2. Right? So let's multiply that out. So this is 1/3 pi times, now this is r over 2 times r over 2 times h over 2. So if we expand all that out, we have 1/3 pi times r squared times h over 8. Okay, and the volume of the cone, the entire cone, is equal to 1/3, this one's easy, right? 1/3 pi r squared times h. So how do those two compare? What would the ratio of those two to one another look like? Okay, so I'm going to rewrite this volume of water. So the volume of water is equal to 1/3 pi r squared h times 1/8. So I just took the divided by 8 out. So you can see that these parts are exactly equal, so that the volume of water is equal to 1/8 the volume of the cone. So that ratio of water to cone is 1:8. The predictions in class were maybe 1/3 or 1/4, but nobody figured it would be 1/8. And that's kind of, sometimes it's hard to visualize in three-dimensional space, but that cone really does continue to go out at quite an angle. So the ratio is 1:8 of water to the entire cone. We talked in class about where this 8 comes from, and it comes from the fact that the cone is twice as tall, and the large cone is twice as tall, and the base has twice the radius too. So this 2 times 2 times 2, or 2 cubed, is the ratio of the, that's where we get that factor of 8 coming out. Okay, so let's just do a quick review. We looked at the volume of a right circular cylinder, and we related that to the volume of a prism, in that they're both the area of the base times the height. And then we were able to take the cylinder and relate that to the cone, and we found that it took 3 cones to fill up a cylinder of the same base and the same height. And so its area formula, or its volume formula, is just 1/3 the volume formula for the right circular cylinder. So it's real convenient for us. It means we don't have to memorize a lot of things. We can just remember them, which is cool. Okay, good luck with the problem set on this, and I hope you will not shy away from any challenge problems.